So, welcome to my presentation for autonomous robotic systems. I shall be talking about a problem in swarm intelligence and my proposed solution to that. So, the problem statement is your customer is a school director who's looking for a swarm of robots that autonomously patrol the hallways of schools. The robots should be patrolling the hallways, checking for children in the hallways, and ask them to show their permission and report the incident via email to the director. So basically, we have to design a swarm intelligence system for patrolling and advise the director of the same. Before talking about the swarm robotics solution, let's talk about what is swarm robotics. It's basically robots working in unison to achieve a common goal. It is a sophisticated collective behavior that emerged from a combination of many simple individuals, each operating autonomously. As defined in the World Congress on Nature and Biologically Inspired Computing, the swarm can solve complex problems that a single individual with simple abilities, computational or physical, cannot solve. The swarm is composed of several individuals, some of which may be lost or can make mistakes, but its performance is not affected. Individuals in a swarm have local sensory information, perform simple actions, have little to no memory. They do not know about the global state of the swarm or its goal. And it especially has an emphasis on decentralized local control and communication. To propose an optimal solution to the problem, we first need to ask some questions to the director of the school. Firstly, the budget constraints. Swarm intelligence can get really expensive, and one of the reasons for less widespread adoption of it is because of the prohibitive costs that come with it. The budget influences the number of robots that can be put into the swarm and the communication mechanisms and which technologies we can use, basically. For instance, detection of humans and localization can be done by using either image processing or by PIR, which is passive infrared sensors. PIR sensors are cheap but provide limited usability when it comes to localization. Cameras, on the other hand, are more sophisticated and can indirectly provide location information, but it requires a lot of processing power on board, which can get really expensive. Secondly, the possibility of students carrying an RFID tag based IDs rather than a written permission of the teacher. This can be recharged when they have to leave the classroom and can be easily detected by the robots when the human comes in close proximity to the RFID sensors. RFID sensors are also pretty inexpensive. Thirdly, whether IR based beacons can be set up around the school. This can provide a means for the robots to localize themselves accurately. However, alternative approaches have been proposed that can use the swarm-based robots to localize themselves using shared knowledge, but this requires the robots to have global communication with each other. There are certain challenges associated with swarm robotics. Firstly, finding the individual behaviors that result in a desired swarm behavior is pretty difficult because we need to do a lot of reverse engineering. Fortunately, the challenge may be addressed because the behavioral rules are supposed to be relatively simple. Often rules are hand designed or sometimes they are evolved. And also making sure that the emergent behavior is stable. Dynamical systems theory can help to characterize and predict swarm behavior because swarm can be described as a system of elements with negative and positive interactions that moves in space and time. However, nonlinear interactions are still hard to model. Thirdly, the resource constraints. The smaller that a device is, the greater the challenge to provide security due to resource constraints because of the storage, communication bandwidth, computational restrictions, and most importantly, energy. Attacks on the provision of resources can lead to the device becoming inoperable permanently. So if the resource is not renewable, this creates a lot of problems. And lastly, physical capture of a robot leads to loss of availability. Worse, capture of security credentials would harm the other members of the swarm if this robot is tampered and introduced into the swarm. Employing control and communication systems systems employing swarm intelligence do not have a hierarchical structure with points of control. The individuals with these systems take decisions autonomously based on local sensing and communications. With such systems, it is evident that there could be many risks if they went out of control. Like, for instance, if Like for instance, if security violations can happen with the loss of confidentiality, swarm robots can interact either explicitly or implicitly. Explicit communication can be achieved via broadcast or RF or directed messages, or RFI and infrared have also been used for explicit communications within the swarms. Other technologies include colored LED display, body language or sign language, color patterns on a robot's body, coil inductions, haptics, audible sounding combination of LED display, to name a few. Implicit communication involves interaction via sensing other robots and their behaviors and interaction via their environment, which acts as a sort of shared memory and is known as stigmergy. And lastly, intrusion detection. When a foreign entity joins a network, it is sometimes called intrusion. One of the challenges in swarm intelligence communication is verifying whether the robot it is communicating with is actually malevolent or benevolent. Let's talk about the potential solutions for the localization. Over the years, several solutions have been proposed, like Thrun et al., which proposes robots to localize themselves in maps created by other robots. But the drawback of this is all robot needs to know all other robots' positions, which can be a constraint if we are restricted to only using local communication. As if we ask the director and if they do not provide a global solution, a communication solution, then we should be only restricted to using local communication. An improvement to this approach was proposed by Fox et al. In 2000, which uses belief-based maps and a hybrid localization approach. In this approach, robots can combine whatever information they have, from cameras to odometry to observed environments and landmarks, to create a belief map. This can work with only local communication, but the drawback here is that all robots need to explore all locations, which can take some time. A third approach was proposed by Howard et al. In 2003, where robots observe each other's motion and create a distributed graph. The robots perform well in dynamic environments, and also partial communication is possible. This was demonstrated in practice by Rubinstein et al. In 2014 by applying it to 1024 kilowatts. The robots used infrared sensors for local communication. Thrun et al. Presented a mapping algorithm where multiple robots can localize in a globally fused map. It required that the approximate initial positions of the robots are known by all other robots, basically. Other potential solutions may be such that if robots have access to internet for sending emails to the director, why not use a centralized server to monitor the systems? And by that I mean like synchronizing the robots, distributing workloads, and ensuring all the robots cover all the areas equally. The drawback with this is the failure of the entire system in case the central server shuts down. And secondly, the scalability of the system. It can work with 10 to 20 robots, but hardware requirements increase exponentially with more number of robots. Secondly, we can use swarms of robots to self-localize themselves based upon landmarks. The drawback with this is hardware to sense distance from beacons is expensive, multiplied by the number of robots. Also, but on the other hand, this provides a better probability for coverage of all locations equally. And a third solution, which was proposed by Eric Hernandez et al. In 2012, was a game theory-based solution where all the robots compete with each other to find out to find the unexplored locations and are rewarded for that, basically. So after considering all the potential solutions, the best approach for this problem seems to be the nature inspired by termites and antbots. Basically, the robot leaves behind chemical trails and is inspired by this paper. But in contrast to this implementation where the robot is trained to follow the chemical trail, in the proposed solution, the robot is trained to avoid the chemical trail. The robots can be programmed manually or may find an optimal solution by exploration. The robots in this solution will be rewarded for finding unexplored locations. In this way, we can ensure that all areas are covered evenly. In practice, implementing actual chemical trails is difficult and unfeasible, so we need something to simulate a virtual chemical trail. Therefore, using any of the approaches mentioned before Each robot needs to have an approximation or a belief of its current position and its previous end positions. Whenever another robot is found in the vicinity with IR sensors or RF, then what it needs to do is exchange its previous locations and beliefs with of all the robots it has encountered and its own. After that, the trajectory is calculated to avoid the other robots and move to a different location. The landmarks may be hard-coded or may be found by exploration as proposed by Howard et al. So I made an implementation based upon the idea which is initially proposed by Claudini et al. Basically, they have proposed a solution for swarm robotics and surveillance systems based on repulsive pheromones. So basically, chemicals which can repel other robots. So this is what the idea is based upon. So this is the algorithmic flow of the proposed solution. Firstly, we need to initialize the system. Then, if any other robot is found in the vicinity, exchange each other's coordinates of beliefs and then calculate the trajectory to avoid the other robot. The previous locations can be sent by local communication like infrared or RF. Then the robot follows a wall until a human is found. When that happens, it should ask for an ID by flashing a light or by speaker. If the human does not cooperate or if the ID presented is invalid, email the director about the incident and the robot's current position. However, there are some potential drawbacks to this approach if the communication is restricted to local only. For instance, if a person leaving the premises encounters multiple robots on their way out, then they will have to authenticate with all of them to avoid getting into trouble, which is hassle, I guess. So I did some simulations and some experiments based upon that. A basic simulation was of the idea proposed by them was tested on the simulator from the assignments. In this, a very basic robot controller was manually implemented for obstacle avoidance and to be repelled by the virtual chemical trail. It also has the random exploratory policy if it does not encounter a wall and if it does not encounter a chemical trail, such that when it has no obstacles or virtual pheromones, it will randomly move around. For the sake of simplicity, in this simulation, all the robots know all other robots' previous 100 locations sampled at 1 second each. So 100 seconds worth of data of previous locations, all the robots know of all the other robots. The robots that each robot knows is not absolute, but it is rather sampled from the Kalman filters and the landmarks visible. As you can see, there are some aqua dots which represent the landmarks, and the robots have their own particular beliefs based upon those locations. And based upon that, a swarm of 64 robots is simulated. A very interesting observation is that the robots behave like random gas particles. Initially, the robot had concentrated at the initial location, but as time progresses and each robot is able to explore more, they diffuse evenly as seen from this video. In my tests, it took about 3 minutes of exploration to get from video 1 to video 2. In practice, this may be reduced by having a genetic algorithm control the robot rather than having the manually coded solution. Let's talk about the significance of this project. This project is mainly intended as a proof of concept and shows that even with very basic code, robots with a sufficiently reasonable swarm patrolling behavior emerges. It does have scope for further optimization and can be tweaked to suit the customer's needs. However, having the robots evenly distribute themselves in an unknown location even without explicit load sharing or task assignment makes this really easy to set up. Also, this model is fault tolerant in the sense that if any of the robots are lost or broken or stolen, it does not affect the entire swarm. And these are the references. Thank you for attending my presentation. Hope you have a good day.